Welcome to Thuwal.
Good morning. Thanks for joining. I'd like to talk to you about a subject I find extremely important and very interesting, and that's our ongoing national discussion on the future energy needs and how those will be met. There's a lot of talk about how we're going to go to a electricity-based economy, but that's where the talk ends, and they never seem to get around to discussing where all that electricity is coming from. So I'll try to explain a little of that and how I hope things might turn out. So we'll get started. All right. Come on. There we go. So for the introduction, if we're speaking of nuclear energy, it's a stable, cost-effective, and zero carbon emission technology for the generation of electricity. So I'll talk about some of the basics of nuclear energy electricity generation, some of the issues surrounding nuclear energy, and changes to the generation of electricity and the challenging demands in the future. So this is just a cartoon of a generic electricity generation. You need some sort of motive force to turn a rotor. It can be steam, gas, water, wind, and whatever it is, it turns a stator, turns the rotor, which is in a stator that generates flow of electricity that goes out into the grid. All right. So here's a nuclear power plant. This is a cartoon of a pressurized water reactor, which is one of the two kinds that are used for the commercial generation of nuclear power in the United States. And it produces clean carbon neutral electricity. The heat's generated in the core, which is, I don't know. Can you see my mouse or no?
No, unfortunately.
Okay. So in that, where's this nuclear power plant, there's on the right of the left of the cartoon, there's the reactor in the core, which is where the heat's generated. That heat's transferred to a steam generator, which the one side of the steam generator is isolated from the nuclear side of it. So it's clean water that goes outside of the containment, or clean steam. It turns the turbine, which turns the electric generator, which makes the power. And then you see the cooling tower down at the bottom right, and that's the any plant, not just nuclear, but any plant that uses steam has to have some sort of cooling to condense the steam to feed it back in. I guess a big point is commercial reactors cannot make bomb grade material, nor do they use bomb grade material. The reactors that we use to produce that bomb grade material are no longer running in the United States. One interesting fact was on January 2nd, Iran announced that it was going to up its enrichment to 20%. And there is no commercial reason whatsoever to enrich that much. So it's strictly their saber rattling, or they're on their way to develop nuclear weapons. So commercial nuclear reactor is not a bomb. Actually, no nuclear reactor is a bomb. They can't explode like a bomb. the reasons they can is you need to have nearly 100% enrichment as opposed to the 3 to 5% enrichment that the reactor fuels have. It's a very difficult design, complex design. Technology needed for it is way out of the reach of just about the whole world. And the hardest part of developing a bomb is having the proper configuration in which to make it explode. The physics in the bomb, the physics don't want to explode. They just want to kind of fizzle away. So you have to go to a lot of effort to make it explode. So risk acceptance, that's, everything we do some sort of risk analysis, whether we realize it or not. So, for example, driving a car, 40,000 Americans die every year in car accidents, and 3 million have to get medical treatment. So we see that as an acceptable risk. So, it's like around here, if you have a nice snowy, icy day, you look outside and say, I don't think I'm going to go anywhere today. That's your doing a risk analysis, saying the risk is too high for the reward. So then, commercial air travel, a lot of people are afraid of it. The last fatality in commercial air travel was in February of 2009. So we've been 22 years since there's been a fatality in commercial air travel. So which activity is riskier?
Is that what you asked?
That's what I said. Yep. All right. So we'll get to radiation. The picture on the right, that shows the electromagnetic spectrum, goes from gamma rays all the way up to radio waves with visible lights in there. So just the normal light we see is part of the radiation spectrum. So I'd say raise your hands if anybody's had a radiation burn, but since I can't see your hands, I won't ask you to do that. So we go. So there's a radiation burn. That guy indulged in some risky behavior and scorched himself sitting out in the sun too much. And as it says, about 7,000 Americans die each year because they like to go out and get a nice tan, and that's the primary cause of melanomas in the country. So to some people, nice bronze body's worth dying for. I was hoping this would show up a little better. This just shows some various radiation doses you can get just from living the life we do. The third column from the right, third column from the left tells us that that's the average American dose. So you end up getting about 630 milligrams a year, which is way below the nuclear workers' dose limit of 5,000 milligrams. But what that shows is we live in an environment where there's radiation. A lot of things we do give us radiation. For example, the far right column, which is very small, shows 2.5 milligrams for flying transatlantic. So that means there's a risk associated with radiation damage just flying to Europe.
Hey Glenn, where does Where does sunbathing fall on that chart?
I looked and could not find any numbers on irradiation dose. All they do is talk about, yeah, what was it? Like wattage per square foot on what hits the ground kind of stuff. And yeah, I don't know. I was real curious to know. But I know people do get radiation burns when they're getting various radiation treatments for cancer. So,
Right.
And that's a pretty healthy dose. So I would assume it's a pretty healthy dose if you're out in the sun all day. But yeah, unfortunately, no numbers. You know, being an engineer, I love numbers. So one of the maybe perceived detriments to nuclear power is how to treat nuclear waste. There is a technical solution on hand, but the political will is not there, and it's primarily the not in my backyard NIMBY syndrome. The preferred way to treat the high-level waste is turn it into glass, which means vitrify it and then bury it in a deep geologic repository. That upper right picture shows this is defense waste being processed. So we are actually processing defense waste into glass logs. You can see those canisters are about 10 feet tall and 2.5 feet in diameter. So they pour the glass into these big stainless steel cans, and then now they just keep them on site. Hopefully someday there will be a central repository for which they can go to. And then, you know, we're not just permanently disposing of any waste, high-level waste at this point. France and Great Britain have been doing it, or the United Kingdom have been doing it for many years. When you talk about how much waste is generated, 1,000 megawatt nuclear plant, which that's enough power for about 850,000 homes, generates 3 cubic meters of high-level waste a year. That's a cube that's about 1.5 meters on the side. I think you could contrast that with a coal-fired plant where 1,000 megawatt coal-fired plant burns about 100 cars a day of coal. Of those 100 cars, 80 of them go out with fly ash. And then got a bunch of other stuff blown up into the atmosphere. So, and you know, a year's worth for nuclear is 3 cubic meters. A year's worth from a coal plant is thousands of cubic or millions of cubic meters. It makes a big mess. One thing about radioactive things is they decay away, and the isotopes which cause or which have the greatest risk are the short-lived ones, and they decay away into not bad stuff in about 100 years. Yucca Mountain was going to be our deep geologic repository. Spent $15 billion on it, and it has yet to receive any waste because politics shut it down. So commercial high-level waste, as defined by the Code of Federal Regulations, is currently being temporarily stored on site at the power plants. So rather than having it deep underground where nobody can get to it, it's now just sitting in above ground storage scattered all around the country. Let's see, I included this picture just to show you, this is an 11th century stained glass windows from a church in Ireland, I think. And when you look at how vibrant the colors are, all those colors come from various metals. For instance, the greens and yellows come from uranium, gold is red, and basically what this shows is that even after 1,000 years, all those metals are still contained within their glass forms. And hopefully 1,000 years ago, the glass wasn't nearly as sophisticated as it is now. So the elephants in the room, it's when people say, is nuclear power safe? There have been no deaths attributable to U.S. commercial nuclear power and no environmental impacts or lasting environmental impacts. So 3 Mile Island Unit 2 happened in 1979. It happened about 3 months before I graduated with degrees in nuclear engineering. So it happened because of steam generator issues caused a partial core meltdown. Some of the radioactive gas was released, but nothing above background was detected off-site. There were no injuries or adverse effects to the plant personnel or the public. And units 1 and 3 operated into 2019. So even on the site of what was the worst nuclear accident in this country, there was nothing to keep anybody from occupying that site. Okay, Chernobyl Unit 4 in 1986. The big thing to remember is Chernobyl is nothing like an American plant. It's designed totally differently, has different physics. Then it does not have a containment building. It was just kind of a reinforced commercial building. And what they were doing was running a badly planned test. They had the safety systems disabled, and they were running it at night so they could get away with everything they weren't supposed to be doing. Kind of the way the former Soviet Union did a lot of things. So it had a steam explosion, which was, because of the physics, it got real hot real fast and it flashed water to steam. And so that steam blew about 5% of the core up and out. So 2 workers died in the steam explosion because they were in there working on the core, and 28 plant and recovery workers died a few weeks later due to acute exposures. Acute exposures were things like, since it was the Soviet Union again, soldiers were brought in to help clean up, and that included they would go and grab pieces of the core with their bare hands with no protection whatsoever and dump them in the dumpster, essentially. And so there were 15, I guess in medical or in epidemiology, you would say 15 additional deaths because of thyroid cancer as a result of the accident. And nothing else has been attributable in the 20 years following. And those thyroid deaths or cancers even are something that would not happen in this country because iodine pills are absorbed, the iodine's absorbed by the thyroid, and iodine is what caused, radioactive iodine is what causes the cancers. So if it's saturated with non-radioactive iodine, you can't get the radioactive iodine in your thyroid. So anyhow, the point is, it wouldn't happen in this country because within defined evacuation zones, there's a big supply of the iodine pills to prevent that kind of thing from happening. Okay, Fukushima Daiichi reactors in 2011 was really kind of a bad design for the backup heat removal systems. They had forewarning that a tidal wave was heading their way, and the reactors were shut down. So they were just sitting there cooling off, and it takes a while for the reactors to cool off. And the emergency diesel generators, which supplied the power for running the residual heat systems, are sitting right there on the beach. And they were designed for a 25 or 30-foot wave, but unfortunately the waves were big enough they flooded the generators, the emergency diesel generators, and then there was no power to drive the pumps and the residual heat removal system. So that's what caused that core, or those core meltdowns. There were no cases of radiation sickness attributed to the accident, and there was some runoff into the Pacific with no adverse effects. Down there, if you run into environmental engineers, one of their favorite sayings is dilution is the solution to pollution. So even though some radioactivity ended up in the Pacific's so huge, by the time it got, say, over to the coast of Washington, it was so diluted it had no effect on anything. So why do we need nuclear power? Electrical demands and sources are changing. There's a need for reliable generation of electricity. It's a robust technology for just about any weather condition, and it has zero carbon emissions. I just like this picture, so I threw it in, but so this is not an actual picture of that's Tesla sitting there in his lab with all that stuff going around him. So how the U.S. currently generates electricity? You can see right now America has quite a portfolio of different technologies for generating its electricity. The graph on the bottom left, you can see coal, which is brown at the bottom, has really been going down, and other things have been coming in to replace it. The big problem is, starting about 2000, so for close to the last 20 years, there's really been no net increase in generating capacity. And then the one on the right shows renewable sources. The interesting thing there is, if you notice, the blue, which is hydroelectric, is pretty much constant, and that's due to the fact that they've pretty much dammed up everything that's worth damming to generate electricity. And in fact, there are movements around to start removing those dams. This capacity factor is basically how much of the time a plant runs at its full or rated capacity. Nuclear is by far the highest, and photovoltaic is the lowest of the major technologies. The point of this slide is if you have 1,000 megawatts, or if you need 1,000 megawatts, you would need almost 4 times as much photovoltaic capacity as you would a nuclear plant. And then this is just showing how generating capacity comes and goes. The upper one shows generators that are taken out of service. By far the largest is for removing coal plants, and yeah, well, I don't have that. Anyhow, and if you look at what we're adding to capacity is wind and solar photovoltaic are by far the two largest contributors, with a little bit of natural gas to fill it out. If you consider capacity factors, net gain and generating capacity is about 10 gigawatts, which is less than 1% of the U.S. generating capacity. So if demand grows more than 1%, we're in deep trouble, and I think it's going to be growing a lot faster than 1%. This is photovoltaic, which is another option for nice green energy. It does a direct conversion of light into electricity, and it's a clean power source when there's sufficient light. Has a few cons depending on how you look at things. It's doped with rare earth elements, most of which are found in China, and most of which is 85% maybe. Its production of electricity is greatly affected by dust, rain, pretty much anything that's on the cells that will start scattering the light. And the place where they like to put them is where it's hot, dry, and dusty. So they have to go to great lengths to keep the things clean. And then obviously they don't generate power at night. So another question is, how do you store excess energy that's generated during the day so you can cover what's happening at night, or when there's storms, or okay. A wind turbine is another option that's quite popular. It generates electricity when the wind blows, and it has no carbon emissions. Some of the cons are if the wind's too low or too high, they're shut down. And that's what a lot of people don't realize is, yeah, the wind can only blow so much, and then they got to shut them all down. Otherwise, the gearing gets destroyed. And I've also never seen any studies on how these things work in or would survive in a tornado, because a lot of them are in tornado-prone areas. Yeah, and the magnets they use in them, about 75% of the cobalt in the magnets is mined in the Democratic Republic of the Congo. So, back in the 70s, 80s, we had blood diamonds. Now I guess we have blood cobalt. The Texas outage recently just showed that icing can cause severe issues with them. And as with solar, you need some kind of storage capacity. And that all comes to battery technology is not where it needs to be to provide a viable backup. So here's one of the big new future demands on the grid, and that's electric cars. And I just did this example based on Tesla's because the data was easy to find. But yeah, Tesla did 500,000 cars last year. And a really important point is this is all new demand on the electrical grid. It may be replacing petroleum products, but the electricity needs to come from somewhere. So it's not a 1-for-1 swap, it's a 1-for-0 swap. And so just putting that many new cars on the road in 1 year took up about 20% of the added capacity from last year. And if all the vehicles on the road, all 273 million vehicles on the road were replaced with Teslas, that would be the equivalent of 144,000 megawatt or 1 gigawatt power plants. And those are the big power generating stations you see. Yeah, I included this just because I think it's real interesting. These 345 kVA lines, those are the picture of them on the left. Those are the ones that distribute power from the generators and are seen, you see them making the long runs across the country. Just kind of as an aside, they apparently cost about $1.5 million a mile, so it's a lot of bucks when you start stringing a lot of lines. And that's one of the things with most power plants, they tend to put them in remote areas because people don't find them aesthetically pleasing, so that really drives up the cost of distribution. The energy mapping system of these big lines, the interesting thing there is if you look at about Denver, you can see that's the only place where the western part of the country is connected to the eastern part. So if there's some generating issues in the west, they're going to have a hard time getting power from anywhere. Yeah, those, and then the little pluses on the border, those are where lines come from outside the country. They're basically 4 power grids, 3 of which, or actually 2 of which are interconnected. Texas has its own grid, and we'll talk about that in a minute. Another thing too, yeah, people like going down to Florida, but Florida only has that one big line, so if it loses some of its local generators because of weather conditions, it's going to have a hard time supplying the power. So yeah, so Texas, I'm sure you all see, what was that, a couple weeks ago when they had that big storm and knocked a lot of their power out. So Texas is the largest energy producer in the country, and almost twice as much as number 2. I think part of that is, I would almost think California would be the most, but California has been shutting down its plants and it's sucking up power from the Pacific Northwest and a large nuclear facility in Arizona. Yeah, so Texas's generation capacity peaks in the summer at 125 gigawatts, and that is a little over 10% of the total U.S. energy production. And it is the largest generator of wind power in the country. This is a map of the Texas outages, kind of when it was at its peak, and in this, the blue is actually good. And it's kind of interesting that up there in the Panhandle, northern Texas, and out by El Paso, where it's high, and they're used to cold, nasty weather, they didn't have any problems with their electrical grid. But when they start getting down south in Texas, where it doesn't usually get cold, things weren't hardened for cold weather. And that's one of the primary reasons they started having all the outages they did. Yeah, so I guess 60% of Texans heat with electricity and the rest use natural gas. So that put tremendous strains on the system because houses in Texas are not designed for cold. They're designed to let heat out because it's usually way too hot. And so, you know, what normally might be a little bit of a drain on the system became a huge drain on the system that never shut off. And that's caused cascading failures. The wind generation fell down to less than a percent of its generating capacity because it could have been at night when the wind wasn't blowing or icing, and winds are too high when the fronts come through, so they had some issues there. The South Texas Project Unit 1, which is down by Houston, was tripped due to a sensor line low temperature, and they just tripped the reactor because, or as a precaution, came online after a couple days. And yeah, before that, for the previous 2 years, it was running at 97.2% of its capacity. That kind of shows this was a line that was outside the reactor and wasn't really made or wasn't designed to operate in extended cold conditions. And that's how most things in Texas are. They don't expect to be cold, or if it's cold, it'll just be during the night and then it'll warm up during the day. So you come up with the question of what do we start needing to protect? Do we need to cold harden everything for a 100-year or 500-year event? And with its costs, that can be quite high. So that's, you know, those are kind of the things people got to start thinking about these days. And I thought it was interesting in January of 2021, the Electric Power Research Institute, which is kind of a independent research lab for the utility industry, where the various utilities are members of the institute, published a report about what are the impacts of extreme events. So I guess they published it a little too late for anybody to do anything about this recent issue. So the takeaways. Electrical demand will increase greatly in the coming years. You got to add new capacity in addition to replacing retired capacity. So you can't just build new plants. You got to replace the ones you're taking out. The distribution has to become more robust to handle greater demand. And I guess one thing I should have said, it also needs to become more hardened against cyber attacks. We certainly want a carbon neutral energy system. And then the Texas imbroglio showed decisions based on risk management can have adverse effects, because basically you're throwing the dice and say, oh, this isn't going to happen, so I don't have to protect against it. And if you happen to be around when the adverse consequence or adverse event happens, then it's too bad you lose. And I would say at this point, nuclear power generation provides the best option, because it's, you know, the stable, it's a stable and mature technology that can supply a continuous baseline energy load. And that's about it. If you have any questions.
Glenn, when it comes to these big transmission lines, how efficient are they for long distance power supply?
They're They're pretty efficient, I think. You know, there's that whole argument that Tesla and Edison had over AC versus DC, because you have to, and I think the reason Tesla won out with the AC is because it's much more efficient over the long distances which we have to transmit power in this country. You know, so maybe European countries where they're so much smaller, they can get away with some different technology, but for us, you know, it's, $1.5 million a mile is pretty expensive, but I guess we can afford the loss based on that cost.
This is Beverly Bodum. How likely is it that nuclear power would come back as one of the major sources of energy?
Well, I think now, well, I know the former head of Greenpeace is now even a nuclear fan, as you know, we've found, or there are ways to take care of the waste, and it has an unparalleled safety record. One of the issues is the plants that are all running were designed in the 70s and 80s, so they have taken none of the technical advances, well, the big design advances in the last 40 years. So there are 3 or 4 new reactor designs that are being out to, is it 3 or 4? Yeah, the reactor designs that are being evaluated by the Nuclear Regulatory Commission are smaller, inherently safe, meaning the physics are designed so that they can't melt down. And I think even Bill Gates is pushing some sort of reactor. I have just heard a little bit about it. But so there are lots of, I think there's a good chance, and I guess I hope we do something, because the, you know, solar and wind they're not what's called base load. You always need to have some plants running, and you know, nuclear is really the only carbon neutral technology we have at the moment that we can run, and we need to start doing something now, because we're taking big plants offline, and it takes a while to replace them. You know, so even if they start building plants, you're probably looking 5-10 years down the line, even if it were coal-fired plants. So I think there's a good chance. There's still a lot of, you know, negative thoughts about nuclear power that I don't think are warranted. So we'll have to see what happens.
Quite a few years ago, I attended the decommissioning of the Northwest Michigan Lower Peninsula power plant, or nuclear plant. That was a huge, they had many people there.
Oh, I'm sure.
Level and, yeah.
Yep.
Glenn, there's a chat question about our statement. So, can you read that?
Hang on. Here we go. Other than politics. Oh, yeah, I guess kind of the same question. I don't think so. I think it's all political. I think the technology's matured at this point, that it's, I said, unparalleled safety record. You know, it's, you know, you think, oh, the coal plants, well, they're pretty safe, but, you know, what about all the coal miners who died of black lung or in mining accidents? You know, that's, so again, we're getting back to the risk analysis, and what risk am I willing to take? And I guess from my point of view, nuclear is our smallest risk at this time. You know, I think the other big push we need is start working on our battery technology, because we got to store those other forms of energy if they're going to become viable over the long haul.
Well, again, this is Richard Bremer. Again, from my perspective, one of the major issues is electric distribution systems. If we're going to have the amount of electric technology to hook up to the grid is far too small to handle all of the projected needs, and that's a huge not only infrastructure cost, but the resistance to putting up major power lines is very large. Also, from nobody wants it in my backyard perspective.
Yeah, and I think part of the here too is it's going to make it very peaky, meaning, you know, everybody drives their electric car home and then plugs it in. So, you know, at 5 o'clock or 6 o'clock, you're going to see some huge increase in the demand on the system. And, you know, the wind drops off at night and it gets dark. So wind and solar aren't going to be there generating the power when you need it. So you need something that's going to generate that power so you can drive your electric car to work in the morning. And that's, again, I'll say again, the problem with batteries. When I was out in Washington State, I had a electric car, and, you know, when the temperature got down into the 10s or below zero, the battery efficiency dropped off maybe 40–50%. So, you know, the range of my car went from 250 miles to 100 miles. So they need to start doing something about that stuff.
Yeah, this is Richard Bremer again. I totally agree. The battery, I did a little bit of work when GM had the electric car fleet out in California in, it was the 90s or 80s or something, a long time ago. But the reason they were down there is because it didn't get cold.
Yeah.
You're in Michigan, northern Michigan, you had a problem, especially if you weren't in a heated garage. So, yeah, I think the whole issue around electricity is there's a whole lot of assumptions and really ignorance on the part of the general public as to what it takes to really get power into your house. Another article I read recently, if you take your electric car and plug it in when you get home into the fast charge system, it takes 5 houses worth of electricity to charge it up. And so if you multiply that by a few, your neighborhood's going to start having problems, I think. So
yeah,
the whole infrastructure issues needs to be dealt with along with the generation aspect.
Yeah, I think one of the issues, because I think I saw maybe GM even is starting to come up with some electric trucks.
Right.
And, you know, it takes forever to charge those things up. You know, if it's 5 or 10 hours, if you got some long haul truck driver, they're not going to make money if they got to stop every 300 or 400 miles to charge up for 10 hours.
Yeah, I think the big truck folks are looking at fuel cells and hydrogen or using hydrogen from what I've read, because exactly right, the battery technology doesn't support a lot of different kinds of way we currently think about how we handle transportation.
Oh yeah, yeah, by the mile. You said you don't make money.
Right.
Actually, Savannah River National Labs, one of the leading hydrogen car developers.
Right. There's a couple big truck companies who bought up technology to like Mercedes, I think, has a big effort going on, and Peterbilt and some other folks for coming up with alternative systems to power trucks that are carbon neutral.
It just kind of as a sidelight, the hydrogen storage for those batteries is a daughter of weapons development. That's kind of a direct application of some technologies that were developed for weapons production.
Yeah, I had trying to store high pressure gases is not a simple system.
Yeah, that's why this is a non-pressurized system.
Oh, okay.
Yeah, some really bizarre physics, but yeah.
Oh, okay. Any other questions that you folks have from Glenn? For Glenn. Okay. Well, Glenn, thanks. It was a very interesting conversation here today, and that's people need to be aware of how fragile their electric systems might actually be. Living in northern Michigan, we find that out occasionally, but when you start having rolling brownout or rolling power outages and all sorts of stuff, life gets more difficult. So
yeah, I've been surprised how stable the grid here in Alpena is.
What's that?
I've been surprised by how stable the grid here in Alpena is.
Well, if you live further out in the country, it might not be as quite as stable. A big, wet, heavy snowstorm took out a lot of power lines down here in Alcona County.
Oh, did it?
Yeah.
Well, that's how we were in South Carolina. Plus, we were the end of the line, literally. So we were usually the last ones to get our power. So that was really the pits. Yeah.
Well, they've done a lot of hardening work up in our area. They've taken the power lines. They used to run the high voltage lines would run bare, and now they've converted a lot of them over to insulated lines, so they can survive some of the trees bending over, stuff like that. But they haven't done that every place. But that's a part of how hard do you make the system?
That's right.
Because it gets. I looked at the cable is like an inch and a half in diameter, and it's multi-layer. It's got a steel covering over. I'm not sure what they actually use for the conductor, but it's a huge piece of wire.
Oh yeah.
Anyways, we'll let you go. Thank you very much. Any further questions? If not, we'll end the program. Thanks to all of you for attending.
All right.
Bye.
Thanks. Appreciate you coming.